Welcome to the 10th lecture of the classical mechanics. So in this lecture, we will look at a new concept called D'Alembert's principle of virtual work. And then we will solve a problem related to this virtual work so that you can understand the concept why we need this virtual work. And then we will try to prove the Newton's law and then go up to Lagrangian that you can end up by following certain procedures. So then you will understand that it's all the same picture for solving the problem, whether you look at it from Newtonian or you look at it from the Lagrangian point of view with certain conditions. Otherwise, it will come towards a generalized format. Okay, let's move into that. Now, what is virtual displacement? We need to catch the concept clearly. Let's consider a simple pendulum that you see here in this diagram. That if the length of the string that I assume is R, if it is fixed, then you can expect that as a function of time, so this can oscillate in this particular way. So it will oscillate from here to and come back like this. That's very clear. But if the length of the pendulum is allowed to vary, then I have a time dependent constraint. Then after the time dt, the length of the pendulum will now increase to at this point, such that the increased length dr is described as a real displacement of this particular bob in a time dt can be expressed in this particular form, which you are very aware of it and therefore no problem. But then this is the real displacement. Now we are going to introduce a concept called virtual displacement. What is virtual displacement? The virtual displacement of a system is nothing but a change in the configuration of the system as the result of any arbitrary infinitesimal change of the coordinates, which is delta r. Remember, now it is dr here, it is delta r, consistent with the forces and constraints imposed on the system at the given time, instant time t. Then that displacement is called virtual displacement. So what are things saying that? So that means if I consider this is my, say, equilibrium positions at an angle theta, for which my length is r of t. Now we have to make a infinitesimal displacement such that the constraints of the system remains the same, in the sense if I move this pendulum from theta to theta plus delta theta, then if there should be a constraint, then what will happen? Then the length of the pendulum remains unchanged. That is a constraint here. If the length of the pendulum remains unchanged, then this distance that is moved by the defined term called delta r is said to be a virtual displacement. That means you, from the equilibrium, you just displaced to the imaginary distance or infinitesimal distance. Suppose it is the pendulum which is equilibrium or at an angle, you are only slightly disturbing that to a small distance without involving the time factor in the picture. That's very important. So the time should not change. If time changes, then situation would be different. So therefore, the displacement when we talk about as a virtual it is completely different from the real, where you have a physical change in the length, which is also time dependent factor. So therefore, we can rewrite this in a simplest way. If the constraint is not time dependent, which means if the length is not changing, and therefore the real and virtual displacement, this is actually the delta r, which is nothing but actually the dr. Eventually we can say it, or we say it other way, the move the system slightly away from the equilibrium position arbitrarily but consistent with all the constraints. All the constraints here is the length of the pendulum is not changing. So that is what we indirectly say that. Now, in order to consider what exactly the ordinary displacement dr and the virtual displacement delta r, let us understand using a transformation equation. Then you get a concept very clearly, and when we solve the problem, you can even much better understand. Okay, let's consider a system of particles, or you can say in many particles in a system whose position is defined by a vector r1, r2, and up to rn for particle 1 to n. And you know that this can be very generally written as ri, which is nothing but the position vector of the ith particle, which has a generalized coordinate and time. Now, if you take a chain rule for this Ri, then the differentiation functional form will turn out to be dr dri, which is nothing but the partial derivative of Ri with respect to q1 and Ri with respect to q2 and so on up to qn, and Ri with respect to t. And these are all same the generalized coordinates. So therefore, we can write it in this simple fashion that dri is nothing but the summation over 1 to n with the partial derivative of ri with respect to generalized coordinate to the change in the coordinate. I'm sure there is no definite confusion here. Now what we are going to impose a condition saying that for the virtual displacement, the time is frozen. There is no change in the time happen because this displacement is very infinitesimal or imaginary such that the time involved in this is 0. So in that case, what will happen? So we can replace we can put dt is 0 and then replace the dri as a delta ri. Then the virtual displacement turns out to be in this functional form. So it is a very infinitesimal change in the position. So that's why from equilibrium. Now, whenever we say a displacement, then you actually end up in also the work done, because in reality, the real work done is said to be that work done due to a real displacement dr of a particle acted upon by a total force F is given by this way, which is no difficulty. You are very clear with the concept. So dw is F dot dr, and that's very easily understood. Now the same concept, if I can apply to the virtual displacement, then I would be able to end up in a definition for virtual work done. If still not clear, keep waiting. We will clear it very easily later. So here, by taking that instantaneous displacement without allowing the time to change, if you can write the virtual or imaginary work done by the system, then we call it as a delta W, which involves the force with the delta R, which is the virtual displacement. Now, it's only a definition. Now we can explain it. What is the implication of this virtual work done or the virtual displacement in more in detail when we consider a generalized system? So let's look at it. The virtual work done for your system of particles. So let's assume a system of particles where the forces F1 and F2 up to F1 are the forces on 1, 2, 3 and so on nth particle. Then by the definition that we derived delta W, the total virtual work done can be written as delta W, which is nothing but the summation over the Fi dot delta Ri. And this is generally for I varying from 1 to n. Now we know that the force, when you talk about, there are two different kind of forces that we need to consider. So the way we have to consider is that Fi is nothing but now sum of, you have the external forces and also the forces of constraint in the system. So one is you apply on a system, the other one is the constraints that evolve inside the system, and both has to be considered when you say this Fi. So then what happens to the systems? Now let's assume for a dynamical system, we know that the Newton's second law for a single particle guides us as either F equal to ma or m r double dot. Now what is F here? It is the force applied on it. So this also can be taken as a total force. One is the applied external force and then constraint forces. Now to bring back to the concept of virtual work, let us take a dot product with the delta R on both sides so that the virtual displacement can be brought in. So taking a dot product with an infinitesimal virtual displacement delta R on both sides, the term will end up as mr double dot delta R is equal to this functional form. It's still we are in mathematical form, so there's no confusion. And now we can expand this term such that rearrange it. So this will be Fe dot delta R plus Fc dot delta R, and you can rearrange it such that this equation can be written in this form. So bringing Fe to this side is Fe minus mr double dot delta R plus Fc delta R is 0. Now, if we consider as a general case, of system of n particles having virtual displacements for each particle as delta 1, delta r1, delta r2 and so on up to delta rn, then this equation can be generalized for any particle, say ith particle, as Fie minus mi ri double dot delta ri plus Fic dot delta ri is 0. Now we can, if we know for a particular particle, then we can sum for all the particle of a system, then my equation will turn out to be in this functional form. So what it is saying is that there is a term involved for the applied forces on the ith particle, and then there is a term involving for the constraint forces. Now we cannot deal it all together. So let us first take the term due to the constraint forces, understand them, then we can rearrange the whole equation, and then you will be wondering what is going to come out. So let's take the term of constraint forces. So what we are saying is that this is the term representing the total virtual work done by all the constraint forces. Now, for any virtual displacement which is instantaneous, and then taking into all the constraint relations, to keep that imaginary displacement or virtual displacement, then the either individual terms with this summation will turn out to be 0, or the individual term may not be 0, but the total summation as a whole system will turn out to be 0 all the way for a static system. So what we are trying to say is that the work done by the constraint forces for the static system, we can indirectly set to be 0. Is that true? So let's take an example so that we can understand it. So let's take a same pendulum case. Now we know that the pendulum, if I move from theta to theta plus delta theta, then I'm going to a virtual displacement delta r. Now what is the constraint here? The constraint is the length of the pendulum does not change and the tension therefore acting always along the towards this point. So this is how the tension acts to keep the constraint relation. Now if we see the effect of these constraint forces on this virtual displacement, how they look like? That look like in this simplest form. That is the imaginary displacement consisting with this constraint in a given moment. The displacement is always perpendicular to the constraint force. The T and delta R are perpendicular to each other. So therefore, the F, the constraint force dot product with the virtual displacement is simply 0 here. In the same line, we can take another example. I'm sure everybody understand this is a simple dumbbell. So you can have this is this side one, it's a mass are almost same. So the dumbbell, this side it exerts a force F1. Let's say this is 1 and 2. So this will produce a force F1 on 2. Similarly, this of F2 1. Now these are fixed by a constant length of the rod, which is R. So now these equal and opposite forces that working on this to produce the virtual work done should be always 0. If not, then you can imagine what happens to this dumbbell. We can later raise it. So when you say virtual work done by the constraint system is 0, that means the system is not disturbed by the constraint forces. Now let's take another example, output machine. Here you have two masses M1 and M2 connected through a pulley where the length of the string is constrained and the tension is acting along. Now if I move this mass M2 by a virtual displacement, a small displacement which is delta Z2, then you can expect the same thing of the same distance of the delta Z1 to go upward. So in this situation, if I look at it, the constraint is there. So the virtual displacement must be along only this Z direction such that when you move delta Z to downward positively, the delta Z1 goes to upward accordingly. So therefore, in this situation, if you see the constraint forces, here also T dot delta Z1 plus T dot delta Z2, both term exist, but because the delta Z1 and delta Z2 are opposite, the summation of the total virtual work done turns out to be 0. The individual term is not 0, but the total virtual work done by the system is 0. Now you would have asked question now by now, sir, if the virtual work done by the system is 0, what are we going to gain it? You have to solve lot of static structures when you talk about in mechanical, civil engineering, even in some electrical engineering systems, and there you need to find out the condition for virtual work done. So let's take a simple example so that you will understand the question why this virtual work done is very important. For example, here a plane pendulum in equilibrium is shown in the figure below. Now, you all know that the pendulum normally in equilibrium, if it is fixed at a point here, it has to be just straight downside, where there is no angle involved. There is no angle involved. Just, this is the equilibrium position, just hangs vertically downside. I hope there is no doubt on it. But now we are going to keep equilibrium at a position with the angle given theta, some value. Can I hold it equilibrium here? Can we guess an equilibrium here? No, it is not possible. So let's complete it. Then is made by attaching a massless string of fixed length L with to a bob of mass M. Now degrees of freedom we will deal it, and then what are the constraints on its motion? You know, we have already solved it. Now the question is find the force F to keep the pendulum in equilibrium at an angle, which means if you want to hold this pendulum at a given angle, which is actually not a normal equilibrium, the way we see here, if it is said to be an defined equilibrium, then it cannot be just done without applying a force. Force is applied, the system is ideal, work done is 0, total work done is 0. But then you need to know, in order to keep this system to be equilibrium, what is the force that you need to apply? This is very important. So in order to do such, equilibrium structures maintenance, you have to understand this concept of virtual work done. Now, how do we approach the problem? Because it's asked in a variety way. So this is the given situation. So the idea is to first find the degree of freedom. And you know very well here the degree of freedom, because this is in plane. So therefore Z is 0. The number 1 constraint come before that. This is a simple bob mass M. So therefore only one system. So there must be 3 degrees of freedom. But we have constraint number 1, that is Z is 0. The other constraint we have is that the length of the pendulum is not changing, and therefore the second constraint comes with the concept of x square plus y square minus L square is simply 0. So therefore, keeping these 2 constraints, the total degrees of freedom in this system is simply 1, and then the position of the bob can be well explained by using the generalized coordinate theta. So 3 minus 2, which is 1, actually that is theta that you are using it here. Now the second step is transform the formation relations. So you have x equal to L sin theta, y equal to L cos theta. Now we are going to adopt a virtual displacement. That means when I am going to say virtual displacement, we are now going to move the bob by a smallest displacement away from here, keeping the length is fixed. So let's assume that this is my delta theta. So therefore, now the bob is moved along the x direction some and y direction some amount. So let's say this is delta x and this is my delta y. So to make it clear, let's remove carefully. So along the x some movement happen, which is my delta x, along some y, that is delta y. So to get this value of delta x and delta y, since you have already the relation with the x to theta, we can directly get. So when you move this pendulum by a infinitesimal distance delta theta, so theta to either this delta theta or small delta, doesn't matter. So the corresponding change in the x, delta x, is L cos theta delta theta, and similarly for y, this is minus L sin theta delta theta. So you got the value of delta x also. And we already know the virtual work done by the constraint forces are zero in a static system, and therefore we need not worry about the constraint forces. Now we have to only worry about the external forces applied. So what are the external forces applied here? You have a force that is applied by yourself to keep the system equilibrium. The other force would be simply the mg acting on it. So if you want to see, one is tension, that is constraint, and the other one is simply mg. So you have only two force, one is applied externally and the other one is gravity. So therefore, the total virtual work done by the external forces should be vanished if you want to consider to be equilibrium. So that means F dot delta x and mg dot delta y has to be simply 0. So that is what we will eventually get it. So mg is along y direction, F is along x direction. So the total virtual work done by is 0. Now we know the value of delta x, delta y. Now you can substitute it and get the relationship to solve the equation. So we put it, now we can take out the equation in the form of delta theta, and we are assuming a virtual displacement delta theta to happen without time involvement, and therefore the delta theta cannot be 0. Therefore this functional form which is within the bracket has to be 0. That will give us the condition to calculate finally the force that you need to apply to the pendulum to keep the system on a defined equilibrium which is at angle theta. This is the condition. So like this, you would solve many problems when you go on it. But at this moment, this is how we say that why virtual work is very important in solving these, equilibrium structures and static configurations in in a detailed way. Okay, now we'll come back to here. So since we say that the total virtual work done by all the constraint forces is 0, now, if you go back to the previous equation that we discussed, what we had is the total function plus this one. Now, this term is now we are saying out to be 0. So, therefore, I am left out with only this part. And this part is now set to be 0, which is indirectly the principle of virtual work, that's by D'Alembert. So what it says that the sum of differences between the forces that is acting on a system of particles and the time derivative of the momenta of the system itself is projected onto any virtual displacement consistent with the constraints in that system is simply 0. Now, if you look at what is inside actually? It is actually the Newton's second law. Will tell you that the term inside the bracket has to be 0 such that multiplying anything with this term is not going to give you any effect. Now the question is, in such case, how to express the relation in such a way that all the terms in this summation becomes individually 0. So if you want to do so, we need to convert this relationship in terms of generalized coordinate. Generalized coordinate. Now we will get one more generalized term. Let's look at it, how to transfer this so that we can understand this concept very clearly. So what we have is, we have this equation in this form. By taking this, we can simply get rid The constraint forces are out of the game. So that now, since there is no constraint force, the term that E need not be written because the only force you have is a applied forces. So therefore, they can be simply written. Now the question is how to express this individual term to give the summations are 0. To do that, let us take the first term separately and second term separately, and you do some mathematical manipulation to bring into a particular shape, and that's going to tell you beautifully, oh, this is how I'm going to deal it for this proof of Newton's law. So let's take a first term. The first term says on the left side, so it is nothing but sigma of, so summation over Fi, because now we are removing the term Xe because we don't have constraint forces, dot delta Ri. That's the term we have, and we already defined what is delta Ri in this functional format, which you have it. So now let's substitute it in this equation. So what you will have is Fi summation over this term is coming into. Now we can rearrange this term so that these all I terms are put together. In that case, this equation can be rewritten in this way, that summation of summation Fi dot partial derivative of Ri with the Qj to the virtual displacement is nothing but is some functional form. Now what it looks like, if I look at it, this is also a kind of work, because if I take this as a virtual displacement, and this must be a force. Similar to what you see this side, this will also be true for it. If that is true, then we can call this as a virtual work. And if you say that's a virtual work for the generalized system, then the Qj has to be defined as a form called generalized force, not a simple way of simply saying a force. It's called generalized force. So the Qj are called as a generalized forces associated with these generalized coordinates. And obviously the dimension, this is going to end up in giving you work. That's anyway no problem. So we have derived the first term on the D'Alembert's principle turn out to be in this functional form. Now we have to find out what is the second term. So let's look for the second term, what is going to give us. So let's rewrite the second term alone, that is summation over mi ri double dot delta ri. And we know the delta Ri what it is. So put that substitution for delta Ri and just rearrange it. Now you have a term m r double dot partial derivative of r with the q and the virtual displacement delta q. Now we need to resolve this part because this is fixed, this is fixed. We need to find out r double dot partial derivative of r with respect to q. Then we have the result out of it. Now how to deal it? Let us take it separately and arrange this term carefully and go one by one step. So can we write r double dot partial derivative of r by q in a simplest form? How do we write it? That r double dot can be written as dr dot by dt. There is no problem because we are writing in the form of time derivative dr dot by dt. And now this can be written in some other form. Let me show it, then I will explain it. So let me take a function d by dt of a and b. This can be written as, which is what you see here, d by dt of a dot b. I can write as a db by dt plus b dA by dt. Now if I want to bring out in one form of it, keep this. So this is d by dt of ab minus, I bring this term here which is equal to this term. That's what we are exactly doing. So if I take this as a and b, and this is one form of it, a db by dt or b dA by dt, one of the term, the other one would be turning out. It's just a mathematical expression. So that's what we have here. So A is R dot and B is partial derivative of R by Qj. Now we need to play with these terms by playing it. So let's take this term in different form of it. Now the same R dot is written here. There is no confusion. But now we are introducing a new change. Here we had partial derivative of R with respect to the Q. Now we are changing into partial derivative of R dot with the Q dot. So we are replacing R by Q to R dot by Q dot. We call this process as dot cancellation. I will come back to that. On the right side, we have another term which can be exchanged the coordinate of it. Here what we have, the d by dt of partial derivative of R by Q, which I can rewrite, take out the partial derivative outside, move the d by dt to inside, then I can rewrite this term in this functional form. This is called time and coordinative derivative can be exchanged. We will see that interchange of the order proof later, but you believe that that is working. So therefore, this term altogether I can write it by using this concept called time and coordinate derivative exchange condition. We will prove it, then you will catch. So I'll prove that later, but we can write it. And as I said here, this is a dot cancellation. Either you can write this partial derivative without dots or with dot, both will have the same answer. And just to bring to some functional form of it. We will also prove this dot cancellation soon in next few slides. So I can take out this one in a different way of it such that here also Ri, here also Ri dot. So I can take this as a Ri dot square or some other way of it. So if I take out the derivative of q dot to outside, I can this as a, it's like a x square d by dx. Now what will you write? You can write it as a 2x, or if you say this is with the y, so this is tx dy by dx or dx by dy. Let me correct. So what it means, so this is something like the dy by dy of x square, which is nothing but 2x dx by dy. So now the 2 is not there, so I am bringing into this side half. So that is what we are doing it here. And this r dot, we can take it as r dot square and so on. So similarly, the same thing we are doing here, it's also r dot, here r dot. So we can bring it as a half r dot square. So we can totally, this term can be simply written as d by dt of partial derivative with respect to velocity of r dot square minus partial derivative with respect to generalized coordinate with the half r dot square. I think now you can feel something is turning out. Now let us substitute this part in this situation. Now what is coming to be? So we have now the solution, the different form of this functionally. Let's put it here. So that will give us the mi and the whole term in the bracket and the virtual displacement. So since m is constant, I can move it here as well as here. So that can be rewritten simply. So now the m term is taken inside. Now what is this? You can very well understand that is nothing but my kinetic energy. Correct? That's simple. So the second term in the D'Alembert's principle turns out to be in this functional form, whereas the first term what we had earlier is turning out to be this format. Now let's put both the term in the equation, D'Alembert's principle in generalized coordinate, and see what it becomes to be. So let's put it both the part. So this is first part, the second part. So let's write it. So qj delta qj, then the whole term with the delta qj is 0. So since delta qj is the same, so I can take out commonly such that this format still can be minimized in this way. Something like we have come close to a Lagrange is feeling, right? But it's not exactly done. Now, what is the situation here? The situation here is the generalized coordinates are independent here, and therefore all the possible variation of delta qj won't be 0. So that means you will not say this is 0, and if the whole term has to be 0, then I can only say this term supposed to be 0. If this term supposed to be 0, I can take out the qj to the right side of my 0 term. So my equation in general form turns out to be like this. Correct? Now that q that you see here is the generalized force format is given. And in order to bring it to a simplest form, let us assume that the force that you consider here is simply conservative. If it is a conservative, what is the functional form of force with respect to potential energy? F is minus del U. So can we substitute and see what would happen? So in place of Fi, now we are bringing the generalized form of the minus del U, assuming the forces are conservative. So that now the generalized forces coming in minus del Ui dot the partial derivative of R with the Q. And anyway, we all know this is the del function, this is a potential energy U, so it also has xy component, and R is defined, so we can now minimize this term effectively. So let's see how to minimize it. So what we are going to get, this is minus dou U by dou xi, dou U by dou y, dou U by dou z, and this is the dou ri by qj means dou xi by dou q, dou y by dou q, and so on. So you can take a dot product with the ii is 1, ij is 0, so therefore jj comes here and kk comes here. So now you can take out these terms and you can simplify it. So what is eventually turning up beautifully that it is minus summation of dou u by dou qj, or now I is for only ui. So if I take it, that is the total potential energy that's as a function of the generalized coordinate. That's well known, because if your forces are conservative, my functional form of force can be written as minus del u, which is actually the true. Now if that is written, now the qj format has come out to be minus the partial derivative of potential energy with respect to generalized coordinate. Let us substitute it here and then see what is happening in this equation. So if I substitute here, we have minus dou u. Now you see this potential energy in a conservative case, it only depends on position, not the velocity. If it is not depending on velocity, can we write it as the partial derivative of potential energy with respect to q dot is 0? If that is 0, so I can bring u term, because anyway it is going to be 0 here. I can take out this u term to this side, so we can write it. Now T minus u is nothing but L. And now if I am having a situation where the forces are conservative, giving the potential energy, and this is the equation that you end up, which was the case we have discussed earlier. The Lagrangian will end up with T minus u, where the u does not depend on the velocity coordinate. Now we have reached the Lagrangian equation from D'Alembert's principle, which is nothing but the Newton's law, F minus ma. Now, to complete the discussion, okay, so that's a thumbs up. So we reach somewhere to get a solution. You don't need to memorize, don't worry, because the question you posed earlier, what is the correlation between the Newtonian to the Lagrangian? The way you solve in Newtonian, you do not take the feeling in Lagrangian, but actually both are indirectly the same picture that we are trying to show it here. Okay, now let's confirm two things we have not solved. The dot cancellation, where the partial derivative of r with respect to q is the same as the partial derivative of r dot with respect to q dot, that we have agreed. So how do we confirm it? So let's take a generalized position vector Ri. Now do the chain rule dRi. So you know that partially Ri with Q1 and Q2, Qn. So this can be simply written as, now we need to find dr by dt, right? That is r dot I. We are trying to get this format, r dot I. So taking a derivative of Ri with this dRi by dt. So this is Q1. So this is Q1 by dt. So therefore it will Q dot. This is Q2 dot, Qn dot, and so on. So that is how it turns out to be. So if it is there, then there should be a dt here, right? Yeah. Now, taking partial differentiation on both sides with respect to q dot. So what will turn up? I have q dot here, that gets simply out. Here also out, out. But there is no q dot here. So this term will eventually, taking a derivative with respect to q dot, will turn out to be 0. So what is this form? That form is same as partial derivative of Ri with Qi. So that's how the dot cancellation can be brought in by taking the partial derivative. So the differentiation only to the explicit time function. You see, there is no time function there. If time function is there, it's not possible. So when that condition, this is valid. Similarly, the second assumption that we have considered is interchange of order of differential operators. So here the d by dt, or partial derivative of dou by dou q, we have interchanged it and brought this functional form. So to do the same, again we'll consider the position vector Ri and take a chain rule process for Ri, which we did just now. And then taking again, now we are doing the right hand side. So r dot is there. Now we are going to take a derivative with respect to q, partial derivative. So therefore this will be dou square r by dou q1 dou qj, and so on and so on. This will come out to be like this. Now let's take the left hand side. If you take the left hand side, which is d by dt of partial derivative of dou ri by dou qj, which is there. Now how to write it? So I can write it d by dt term as the change of the derivative dou by dou q1, and this way. So you can bring it. And now this can be expanded so that this is dou square by r by dou q dou qj. So where the right side, this term and this term is the same, the second term is same, third term is same, and fourth term is same. So therefore, for a function of a potential or any form, the partial derivative with respect to generalized coordinate can be interchanged easily with the order. So that's what these two proof helps you to bring all the functional form. So now if we rewind back what we have done in this class, so we started from the simple concept of virtual displacement and associated virtual work done, and then bringing this Newton's law for a particle of a system, and then putting together with the virtual displacement, entertaining to the constraint forces of a given static system to be 0, and that letting the first term in this equation bringing into a generalized coordinate system for a more generalized expression with the qj. Now considering the q is due to only conservative force, we could easily reach the point that it is nothing but we come towards the Lagrange's equation. Then you may have a question in mind, okay, now I consider the forces are conservative. Now what happens if my forces are non-conservative, right? Or if my system experiences both conservative and non-conservative forces. In such case, this Q has to be resolved depending on whether I have conservative force or non-conservative force, and then once you resolve it, we should be able to solve the problem accordingly. And those problems involving constrained and non-constrained forces we will discuss in the next class. But for your tutorial, we take the virtual work concept and try to solve. So I will give 3 problems to solve in the tutorial, and also will give additional problem, and your quiz 1 also will be discussed in the tutorial, so that you know what is done in the quiz 1. So with that, we will stop here and we'll take the questions if any you have it.